Welcome back, AP Stat. This is part 2 of Boot Camp number 1 free response featuring problems from the 2018 AP exam. So we're going to pick up with problem number 4. The anterior cruciate ligament, which is ACL, is one of the ligaments that help stabilize the knee. Surgery is often recommended if the ACL is completely torn, and recovery time from the surgery can be lengthy. A medical center developed a new surgical procedure designed to reduce the average recovery time from the surgery. To test the effectiveness of the new procedure, a study was conducted in which 210 patients needing surgery to repair a torn ACL were randomly selected, or that is assigned, to receive either a standard procedure or the new procedure. Based on the design of the study, would a statistically significant result allow the medical center to conclude that the new procedure causes a reduction in recovery time compared to the standard procedure for patients similar to those in the study? Explain your answer. Okay, so that's part A. Think about how you would answer part A. Pause the video and unpause when you have an answer. Okay, let's look at our answer for part A. The answer is yes. The patients, the problem says, were randomly assigned to receive either the standard or new procedure. So we have a clear control and treatment group, which reduces the chance of a confounding variable affecting the results, that is, the randomization does. Therefore, for patients similar to those in the study, the medical center could conclude that the new procedure causes a reduction in recovery time compared to the standard procedure with a statistically significant result. So essentially, since this is a well-designed experiment, right? This is not a mere observational study. This is a well-designed experiment. A statistically significant result would signal causation, not just association, causation. Okay, now let's look at part B. Summary statistics on the recovery times from the surgery are shown in the table below. Do the data provide convincing statistical evidence that those who receive the new procedures will have less recovery time from the surgery, on average, than those who receive the standard procedure for patients similar to those in the study, right? Now this one's going to take a little while because this one is, as you can imagine, a hypothesis test. See if you can figure out what hypothesis test we should do and lay out all the necessary components of a hypothesis test. Okay? Pause the video, give this one a go, unpause when you're done. Okay, I'll assume we're ready to look at this hypothesis test for part B. We're going to let mu sub s denote the mean recovery time among patients similar to those in the study if they receive the standard treatment. So S for standard. Let mu sub n denote the mean recovery time among patients similar to those in the study if they receive the new treatment, right? So the null hypothesis is that the mean recovery time for patients similar to those in the study, given the standard procedure, is equal to the mean recovery time among patients similar to those in the study if they receive the new treatment. The alternative hypothesis is that the first mean is greater than the second mean. So the standard procedure, on average, for patients similar to those in the study, would take longer than the new procedure. So we're going to use a two-sample t-test for the difference of population means. All right, so that is the study we're doing. It's a two-sample t-test for the difference of means, and those are, of course, population means. So we need to check a couple of conditions. Randomization. Subjects were randomly assigned to the treatments, right? And the sizes of both samples are sufficiently large. If the samples were not sufficiently large, if they were under 30, then we would want to make sure that the histograms for the sample data were bell-shaped. All right, but these samples are very big, and so we're good. All right. And by the way, since this is an experiment, we don't need to check the 10% condition. All right. Moving on. If you were to go into the calculator, your test statistic would be 7.127, and the p-value is about 8.358 times 10 to the negative 12. That is a very, very, very small number, all right? That's a decimal and then 11 zeros, and then you get to the 8, all right? That's not going to happen, okay? So that p-value signals to us what we should do. But before we get to that, let's just make sure that we can get these values in the calculator in the first place. So here we are. First thing we need to do is go to Stat, go to Tests. We're going to go to two-sample t-test. And I've entered all the information here. Our first sample, the standard procedure, has a mean time of 217, and we have 34 is our standard deviation, and our sample size is 110. The mean for the second sample, that is the new procedure, is 186, standard deviation of 29, and sample size is 100. We want to pick this alternative hypothesis that the first mean is greater than the second mean. That is, the mean for the standard procedure is greater than the mean for the new procedure. For pooled, always select no, and we hit calculate. And here are the values that we've seen before. T equals 7.127 approximately, and the p-value is 8.358 approximately times 10 to the negative 12. Very, very small p-value. So how should we summarize our results? The p-value is low, so we should reject the null hypothesis. There is convincing statistical evidence that the mean recovery time, will be less for the new procedure than for the standard procedure. Here's the next question. The following histograms summarize the teaching year for teachers at two high schools, A and B. Teaching year is recorded as an integer, right? So no decimal values allowed. With first-year teachers recorded as 1, second-year teachers recorded as 2, and so on. Both sets of data have a mean teaching year of 8.2, with data recorded from 200 teachers at high school A and 221 teachers at high school B. On the histograms, each interval represents possible integer values from the left endpoint up to, but not including, the right endpoint. Now let's look at A. The median teaching year for one high school is 6, and the median teaching year for the other high school is 7. Identify which high school has each median and justify your answer. Okay? So consider those two histograms and consider which has the median of 6 and which has the median of 7. All right, I'll assume we're ready to continue, that you've paused the video and tried it on your own. Here we go. The median teaching year for high school A is the mean of the 100th and 101st data value from least to greatest. Why is that? Because there are 200 teachers at school A, all right? This value would be from 7 to 10. If you were to count starting from the left, once you get to that 100th or 101st data value, you would be in the 7 to 10 block. The median teaching year for high school B is the 111th value, all right? That's because at high school B, we have 221 teachers, right? So the median is going to be a particular value, not the mean of two values. It's going to be a particular value, and it's going to be the 111th value. Okay? This value would be somewhere between 4 and 7 if you were to count from the far left over to the right. Somewhere in the 4 to 7 bar, you would find that 111th data value. So this means the median teaching year for high school A would need to be 7, and the median teaching year for high school B would need to be 6. And the reason I know that for certain is that in the histograms, each interval represents the possible integer values from the left endpoint up to, but not including, the right endpoint. So even though high school B features a value in the 4 to 7 block for the 111th value, 7 is not one of those options. All right, so this is high school B is the one that would need to have the median of 6. All right, let's look at letter B. An additional 18 teachers were not included with the data recorded from the 200 teachers in high school A. The mean teaching year of the 18 teachers is 2.5. All right, so younger crew. What is the mean teaching year for all 218 teachers at high school A? All right, give this one a go, try it on your own, and see what you get. All right, I'll assume we're ready to continue, that you've paused and given this a go. Let's look at B. The mean for all 218 teachers at high school A would be the following. We know that for 200 teachers that were sampled, the mean was 8.2. For the 18 additionally sampled, the younger crew, their mean was 2.5. If I were to multiply and then add these two quantities and then divide by 218, I would get the mean for all 218. All right? That's how means work. Remember, a mean is a one number substitute for all the data values in a set, such that if you replaced each one of these 200 data values here with 8.2, there would be the same sum. All right? And if you replace these 18 all with a bunch of 2.5s, the data set would have the same sum. So if you were to add these two quantities together and divide by 218, you get the mean out of 218. All right, let's look at part C. The standard deviation of the teaching year for the 221 teachers at high school B, okay, so other school, is 7.2. If one teacher is selected at random from high school B, what is the probability that the teaching year for the selected teacher will be within one standard deviation of the mean of 8.2? Justify your answer. All right, let's think about how we would do this one. Let's think about how to use that standard deviation in the first place, given that we're working with a histogram. Try this one on your own, see how you do. Pause the video and unpause when you're done. Okay, let's look at part C. Note that 8.2 plus or minus 7.2, that's the mean plus or minus the standard deviation for the sample of 221 teachers from high school B, gives the interval 1 to 15.4. Now that means we should consider the heights of the bars from 1 up to 16. So we start at the lowest bar incidentally and go up to here, including integer values starting at 1 but up to, but not including, 16. The sum of the heights of the 5 bars on that interval divided by 221 yields first bar 79, very close to 80, it's about 79. Second bar 34, very close to 35 but not quite. Third bar 28. On the higher end of the interval from 25 to 30, we'll say 28. Then another 29, then a 19, very close to 20. If you sum all of those and divide by 221, you get 0.8552, right? And that is the answer. And up here we have the justification for the answer. Last but not least, we have the investigative task, right? This one has 5 parts, and this one's a doozy. So here we go. Systolic blood pressure is the amount of pressure that blood exerts on blood vessels while the heart is beating, right? As opposed to diastolic. That's the little number. Systolic's the big number, diastolic's the little number. Moving on. The mean systolic blood pressure for people in the United States is reported to be 122 millimeters of mercury, that's mmHg, millimeters of mercury, with a standard deviation of 15 millimeters of mercury. The wellness department of a large corporation is investigating whether the mean systolic blood pressure of its employees is greater than the reported national mean. A random sample of 100 employees will be selected. The systolic blood pressure of each employee in the sample will be measured, and the sample mean will be calculated. Let mu represent the systolic blood pressure of all employees at the corporation. Consider the following hypotheses. Null hypothesis, mean equals 122. Alternative hypothesis, mean is greater than 122. Now let's look at part A. Describe a type 2 error in the context of the hypothesis test. Give that a go, try it on your own, pause the video, unpause when you're done. Okay, let's see what a type 2 error would look like. The wellness department would commit type 2 error if the mean systolic blood pressure of employees at the company is actually greater than 122 millimeters of mercury, but the wellness department fails to reject the null hypothesis that it is 122 millimeters of mercury, right? So type 2 error, the alternative hypothesis is correct, but we fail to reject the null. And of course, we need to relate it to the situation at hand to get full credit. All right, let's look at part B. And this is where it starts to get really interesting. Assume that sigma, the standard deviation of the systolic blood pressure of all employees at the corporation, is 15 millimeters of mercury. If mu equals 122, the sampling distribution of x bar, that is the sample mean, for samples of size 100 is approximately normal, with a mean of 122 millimeters of mercury and a standard deviation of 1.5 millimeters of mercury. What values of the sample mean x bar would represent sufficient evidence to reject the null hypothesis at the significance level of alpha equals 0.05? All right, so give it a go, try it, or just skip right to the answer. Okay, here comes part B. The z-star critical value that would leave alpha equals 0.05 on the right tail of the standard normal model, if you don't know it already, is inverse norm, and then we would have an area of 0.95 calculated from the far left-hand side of the bell curve, mean of 0, standard deviation of 1. That's standard normal model, 95% shaded, leaving 5% only on the right. That would give a cutoff of 1.645, and that number may well be familiar to you. You may be associating that with a 90% confidence interval using the normal model. I'll let you think about why that's true. This means that we need to find values of x bar such that the z-score is greater than z-star equals 1.645. That is, 1.645 is, this should be strictly less than, my apologies. 1.645 is just less than, not equal to, x bar minus 122 over 1.5. Mean for the population as it appears in our hypotheses, and we have the standard deviation as it appears in part B, and we need to find the mean such that this statement is true. All right? If we were to do some algebra, multiply both sides by 1.5, add 122, we would get 124.4675 millimeters of mercury, and X bar would need to be greater than this threshold in order to register as a significant result at alpha equals 0.05. All right, there's part B. Now let's look at part C. There's a little additional detail before part C. The actual mean systolic blood pressure of all employees at the corporation is in fact 125 millimeters of mercury, not the hypothesized value of 122 millimeters of mercury. And the standard deviation is still 15 millimeters of mercury. So, using the actual mean of 125 millimeters of mercury and the results from part B determine the probability that the null hypothesis will be rejected. So what are the odds that we're going to reject this false null hypothesis? Think about how you would set this up. Try to do this and unpause the video when you're ready to see the answer. Okay, I'll assume we're ready to continue. Here comes part C. We're going to note that X, and it's very faint here, it should say X bar, is a random variable. The sample means a random variable, and it's going to be centered at 125, the true population mean, and it's going to have a standard deviation of 1.5. Same thing going on up here, okay? So the probability that H sub 0 will be rejected is normal CDF, our value that we got from part B, arbitrarily high number for our upper threshold, actual mean is 125, standard deviation is 1.5, and that is approximately equal to 0.64. All right, so 0.64 is approximately the probability we reject that false null hypothesis that the mean systolic blood pressure for the employees at the corporation is 122. Now, let's look at part D. You could have gotten part D without getting any of the other parts of this question. What statistical term is used for the probability found in part C? Think about what statistical term is equivalent to the odds that we reject a false null hypothesis. All right, here comes the answer. The probability in part C is called the power of the test. Power is the word. The power of a hypothesis test is the probability of rejecting a false null hypothesis. All right. And the coup de grace here is E. This is easily, E for easily, the most fun part of this problem. My definition of fun. Suppose the size of the sample of employees to be selected is greater than 100. So we're adjusting the sample size, making it bigger. Would the probability of rejecting the null hypothesis be greater than, less than, or equal to the probability calculated in part C? Okay? That 0.64 number. Explain your reasoning. So give this one a go. See if you can come up with a method to determine whether the probability of rejecting the null hypothesis with a greater sample size would be greater, less than, or equal. Okay, here's the answer for part E. If the sample size is increased, the odds of rejecting the null hypothesis also increases. Increasing the sample size increases the power of a hypothesis test. The bigger the sample size, the bigger the power, all right? Because the sampling distribution of sample means is going to narrow, okay? As sample size increases, the spread of the sampling distribution of sample means is going to get narrower, okay? This means a value for x bar closer to 122 millimeters of mercury than if n is equal to 100 would be a significant result, okay? And since the true mean for the population is 125 millimeters of mercury, rejecting the null hypothesis is all the more probable, okay? So if you increase the sample size past 100, it is easier to attain a significant result, considering that the true mean is 125 as opposed to 122. There you go. There's the investigative task. Hope you enjoyed this. Hope you learned something. See you next time for Boot Camp Free Response number 2.